One of the cool things about being a maker is that often it's the journey to get to your solution that's more important than what the solution really is. And I've been experiencing that over the last couple of months as I've been playing around with a little circuit that I needed to build to deal with a problem that I have in my Zune. So let me tell you a bit about the problem, and then we'll take a look at what I did to solve the issue. So for those of you that aren't familiar with it, and given the commercial success of the Zune, that would probably be a lot of you, the Zune is basically a small hard drive based MP3 player. Pretty common solution to the desire to have large capacity, or at least at the time when these were built. And here you can see some images of the Zune 30, which is the one that I have. It looks like this. I don't have it in brown. I have a white and black one now. But the problem that I was having was that the Zune would drop the USB connection when it got cold. And I wasn't sure whether it was the truck or whether it was the Zune, the cables, what was going on. And I swapped a bunch of stuff around. And eventually I tracked it down to seeing that it was a classic environmental problem. If we have a look at the specifications for the Zune, now I don't have the actual Zune manual anymore, and I couldn't find it looking it on the web. What I do know though is that the hardware was built by Toshiba, and it's basically a Toshiba Gigabeat with some custom buttons and a little bit of cosmetic work to make it look different. So if we have a look at the manual for the Gigabeat, we can zoom into the specifications and we can see that the temperature, operating temperature, is from 5 degrees Celsius to 30 degrees Celsius. Now, the problem I have is that I leave the Zune in my truck and my truck's parked outdoors. So here it gets cold enough that during winter it drops outside of this operating condition range, and my Zune would drop the USB connection, and I'd have to wait until it warmed up. Now, I talked about the journey being the thing more so than the solution. The solution is really that I can get a more modern MP3 player, one that has better environmental specifications, run it in that way, or I can go bring the Zune inside. But instead, what I thought I could do is I could go and build a little heater. Now, when I was looking at the little heater, I sat down and I said, well, okay, I've got Arduinos, I've got Raspberry Pis, I could actually just go get a microcontroller straight from Atmel, build my own thing. But it occurred to me that, really this is a simple problem, and sometimes you don't need a microprocessor or microcontroller to solve the issue. So I wanted to go out and build an analog circuit that would do it. So what I'm going to do now is take you through the evolution of my heater, and you can see what I did and where I ended up. So I knew I needed a heater, and I need a heater of a certain size, and it needed to run on 12 volts. Now, I could go buy a number of different heating pads. I could have sourced them from places like DigiKey or Mouser, or gone to Shenzhen and one of the marketplaces and looked there. But I knew that you could get heaters that were 12 volt driven for heating the handle grips on a motorcycle. So I just happened to lob over to Amazon and do a search for this, and I found this set of heaters. It's basically a handle grip heaters. You can see there's two of them here, and they run on 12 volts, and they have everything you need to if you wanted to put it on a motorcycle. Now, I just needed the heating pads, so I was going to cut those out. That's what I did. I cut them out, and then I used those in my heater. So now that I had the heating pad, I knew that the next thing I need to do is to detect the temperature and provide voltage to the heating pad. So to detect the temperature, I decided I'd just use a simple thermistor. And to detect or to send voltage to the heating pad, I would use a solid state relay. So I went up to DigiKey and I had a look around, and I found this little NTC Thermistor from Vishay components, and I was able to buy a handful of these to play around with. Now, these devices here, the one I have is a 10K one. So if we scroll down here to table 3, what you'll see is it's set at a ambient temperature of 25 degrees. And so when it's at that temperature, it'll have a resistance of 10 kiloohms. The reason I chose something around that range was because how I'm going to end up using it is to read a voltage across this thermistor. So I want to be able to set up and read that voltage. And having a nice high resistance means that I'll get very minimal current flowing through that thermistor when I have it plugged in. Now, the next thing that I needed to do was to turn on the power to the heater. And so how I was going to do that was to use a solid-state relay. And I happened to go looking for a relay. And again, Vishay seemed to have a reasonable product. And so I bought this little relay. Now, I know it will work for 12 volts because I can see the voltage range in here, and I know that it handles DC, and it will handle up to 2 amps of current. And I thought that would be enough because I measured the voltage, I measured the resistance of the heating pad, and it was about 14, 15 ohms. And when you do the math on that, that means it'll draw about 750 milliamps. So I wanted to have a bit of headroom just in case as the resistance changed, the amperage draw changed. And I could drive this off my analog circuit. Now, once I had that thermistor giving me a voltage, and then I had my solid-state relay, I needed something to be able to make a decision as to whether to turn on or turn off the relay. And I had already here at home a bunch of these LM358 operational amplifiers. And these operational amplifiers, if you remember Rule 1 for op amps, is that they will do everything they possibly can to ensure that their inputs are matched. And I can use that, and in fact I can use it as a comparator to detect the different voltages between what I would like the temperature set to be and what the temperature reading actually is, and then have it either go to the supply rail or go to ground, and use that to turn on the solid-state relay. So let's have a look at how the circuit would lay out. So let's take a quick look at the circuit before we actually go see it in operation. This is the simple circuit. That's all I needed to set up. I have a 12 volt coming in. I have the LM358 there. I'm using only one of the op amps. I'm using the op amp as a comparator because you can see there's no feedback. And I have a connector for the thermistor, and I have a resistor here. And you can see that resistor 3 is 18K. Now, why did I choose 18K? Well, the reason I chose 18K was that the operating range of the Zune is 5 to 30 odd degrees Celsius. And so I wanted to make sure the Zune would stay warm. And if we go back and have a look at the data sheet here, I can see that when I get down to 10 degrees, the thermistor will have a reading of 18K. So at 18K, I'm basically going to have 6 volts split across there, and I can set the potentiometer to be 6 volts so that when I drop below 6 volts, this will turn on, and then I turn on the solid-state relay, which enables the current to flow through the heater. So it's a pretty simple circuit. Let's take a look at it in operation. Okay, so here's the circuit that I have set up, and in the background here you can see the meter, and I'm just reading DC voltage. What you have right here is the potentiometer, the 3296. I have the thermistor right here, and that's set up as a voltage divider along with the 18K resistor. Those voltages will feed in over here to my LM358, which then sends that turn on or turn off voltage down to the solid state relay. And the solid state relay turns on, and you can see that it puts it out to my two little micro grabbers here, which I actually have connected to my electronic load, and it's set to draw 750 amps, which is the roughly the current that I would expect when I'm actually running the heater. So we have a look at the voltages here. We can see that the thermistor, if we drop in here, you'll see the voltage of 7.47. And if I put my hands on the thermistor and get the cable out of the way, you'll see that as it warms up, the voltage increases. And eventually that voltage will cross the voltage that I have set by the potentiometer. So if we go over here and actually have a look at the inputs on the LM358, we can see that the voltage that's coming in from we can see the voltage coming in from the thermistor, and I can show you that changing. We can see the voltage coming in from the potentiometer, and now it's set because I set it at 7.87. Now, why I set it there is so that it works in the ambient temperature here. And if we have a look at the output, what you'll see is that we're outputting about 8.6 volts. And if I warm up the thermistor, you'll see that it does the comparison. It drives it back down to 0, or the ground rail, when it needs to try and send things negative. And then eventually that thermistor will cool down from my body temperature, and it will turn the system back on, and you'll see it there just turn on. Now, if we come over here and have a look at what is going to the load, you can see that what I have here is when it's turned on, the voltage drop across the solid state relay is about 250 millivolts. And if we turn it on, we'll see that we turn it off. Now that the solid state relay has disconnected, the effective voltage, because there's no current flowing through here across the load, is going to be 12 volt, which is what I have set as my rail. And when I let go of that, if we sit here and watch it for long enough, what we'll see is that it will drop again to about 250 millivolts across the relay. So we saw the circuit here in operation, and it's a fairly simple circuit, and I wanted to take this and move this into something that I could use in my truck. So to do that, the first step I needed to do was to go spin up my own PCB. Now, you can do that inside a dip trace. It's a great package. Just go and convert the PCB and it will spit out one, but I've already done that. And so this is the board as it ended up being designed. Now, the first time I did it, had it lay out and do some stuff, and I had to make a couple of changes just to get it to lay out better and fit inside the box. But here you can see I have my 12 volt in, I have the potentiometer, I have the solid state relay, the LM358, my voltage divider network, and here's where I'm going to connect the heater and the thermistor in. Now I'm using some components that, some little connectors that will just let me push the cables in and plug them down, or at least that was my plan. And if we have a look at how the board would look in real life, here you see what the board would look like. And so this gives me a way of, looking at the individual components and seeing that is it going to lay out properly. And here you can see the little connectors that I'd put the cable through, and they just crimp down on top of the top of the cable. So let's have a look at that, how it actually came out. So this was the original Zune heater layout, and you can see this is version 1.1, even though the PCB layout I showed you was 1.2. I had to round off the corners to get it to fit into the box. And when I populate all of these items, what you end up with is a circuit that looks like this. Now you'll notice that I don't have the connectors in, and the reason for this is that after I bought the connectors, you saw the little connectors, they didn't give a great, the gauge of the wire is a little too small, so they didn't give a great experience and reliable connection. So what I ended up doing, just for the purposes of testing the device, was soldering these directly in to the circuit instead. So here you can see the, I have the potentiometer. I could feed in my 12 volt here and drive the heating pad and get pretty good results. The heating pad will heat up, to about 50 to 60 degrees. So it's nice, warm, it's hot. You don't really particularly want to hold it, but it doesn't have a lot of thermal mass to it. So it's not holding it. It drops that high temperature very, very quickly and becomes a very gentle heating approach, which is what you would expect given that you're going to be holding those handlebars. So that was how it came out, and you can see that the 3D render was fairly accurate. But I realized I needed to make some changes to it. So I wanted to make three primary changes. One, I wanted to ensure that I had clean power. Two, I wanted to move to a fixed activation point. And three, I wanted to change from through-hole to surface mount components. So let's have a look at the new schematic. Here you can see the new schematic, and it includes this portion over here, which is the power supply. It's providing clean 12 volt power over to the rest of the circuit. In the circuit here now, I have my thermistor in a voltage divider, so it's now a guaranteed set point compared to this set point over here. The reason that I made those changes is firstly clean power because of the automotive environment. You think about connecting to a car and you're really thinking about, I'm plugging it into a battery and it's 12 volt coming from the battery. Well, that's true when the vehicle is off, but when the vehicle's running, you're going to suffer a bunch of different transients. Let's have a look at a little typical graph for the automotive transients. When the alternator is running, you're going to get 13.8, 14 volt nominal. But then you're going to get difference in what you'll see on that network when you turn the crank off, when you stop turning or trying to start the car, you'll get a load dump, you get noise, you get jump start, reverse battery transients. In fact, this is such a typical sort of waveform that a lot of arbitrary waveform generators will have this as a noise type that you can go in and select and add to your waveform generator output to utilize to check your device. So to make the system clean, what I wanted to do was to adopt an automotive part, an LM2596. And this is basically a DC to DC converter. And it will take whatever power's coming in and put 12 volt on the output, assuming that the incoming power is higher than 12 volt. I purchased the LM2596 12, which is fixed 12 volts, so that I didn't need any additional circuitry to handle setting up the reference voltages and controlling that. And so here you can see this is the device. I have some filter capacitors, a Schottky diode, inductor. That all helps give a nice clean power output. And according to the math that I did, I should be seeing ripple on that clean output in the 30 millivolt range, which is certainly nothing that I need to worry about given the simplicity of the circuit over here. The second thing that I talked about that I wanted to do was to adopt a fixed operating point. And the reason I did that is it occurred to me that once I put the device in my truck and I set the temperature that I wanted it to turn on, then I'm never going to need to set that pot again. And in fact, I'm going to have to keep checking it in case it gets bumped or moved. And so rather than doing that, what I did is just simply set up 2 voltage dividers here, the thermistor in series with the R1, and then R2, R3. And they're all set up so that the voltage that comes in, when I get around the 10-degree mark, the voltage from the thermistor in series with 18K should be equal to the split 18K here. And this way I can have one component type, these 18K resistors, just coming straight into the comparator, and then the rest of the circuit acts like it normally does. The final thing is I had never done any surface mount work before. I had seen surface mount boards. I had used breakout boards that had breadboard adapters on them and so on. And I was familiar with the technology, but I personally had never actually assembled or designed a board that would work that way. So I wanted to do that and experience. Now, this is massive overkill for the project that I'm doing, but this is what I was talking about at the start of the video. It's more about the journey than really the destination. I had a chance to try out something new with a surface mount and experience creating a clean automotive power supply. So let's have a look at what this turned out to be when I actually did the PCB on it. So let me just open up the DipTrace PCB layout again and open up that layout. And here you can see what the new layout looks like. And all of this componentry over here is the new power supply componentry. This is basically the solid state relay and the op amps, and I have the heaters and the thermistor. I was still planning on using those RTC components, using those little crimp headers, because I hadn't actually received them yet at this time. So I hadn't discovered that they wouldn't crimp onto the cables reliably, or at least for my application. So this is sort of a trap, clearly, for people that are new to it, is picking your components and spinning boards and so on. You really need to be certain that the components are going to be the one that you're going to use. So as it turned out, it doesn't really matter because they were through-hole components anyway, so I can just solder both the heater and the thermistor direct to the PCB. Here you can see the LM2596 package that I have, and I've created a bunch of vias in the ground plane here to help utilize the PCB as the heatsink. And I actually ran this, and we'll have a look at the actual working device. But I ran this for several hours at full power, both at 13.8 nominal as well as 12 volt that I would get off the battery. And in both cases, the DC to DC converter maxed out at around 50 degrees Celsius there, which, if I did the math and looked at it, I'd probably find a junction temperature well below 100 degrees, which is inside the operating specs in the data sheet for the junction temperature of the device. So overall, utilizing the PCB as the heatsink works for me in this case. Your mileage may vary if you go and use this somewhere else. So let's have a look at the actual device. So this is what the new PCB looks like now. You can see that it's got the vias to turn it all into a heatsink. We have the surface mount layouts and the existing circuitry that we've all seen. So when you actually populate that up, what it ends up looking like is something like this. Now, I haven't populated the through-hole components. This is all just the surface mount stuff here, and you can see the solder paste has come through those vias from underneath this package that is bonding helping transfer the heat into the ground plane to use it as a heat sink. So to run this, what I can do is go and hook this up just like I did before, and here is the thing hooked up. I have the heater pad, I have the thermistor here. This is the little 12-volt input, and what I can't do, because it's a fixed item, I don't want to go get an ice cube and start cooling that down. I can't actually get this circuitry to turn on, but we've already tested this circuitry extensively, both on the prototype board as well as in the through-hole version, because I have not changed that. I just simply utilize the same parts. Now, I did actually test this, but for this purpose here, what I have is I have my load now just connected to the output of the power supply. So I can effectively bypass the solid-state relay and test the output. So let's turn that power on, and you should see the little green LEDs come on here. And let me turn my load on, and now I'm bringing in power from through this, and it's being cleaned up and provided here. And I can see that I'm generating about 8 or so watts off my 750 milliamp load. Let's take a quick look at what the power on that clean rail actually looks like. Okay, so what I've got now is I've just got my oscilloscope all set up, and I've clipped into ground, and I'm just going to probe the power and see what comes out there. So let's just reset that. Okay, and 5 microseconds, that's a little too much. Let's bring that together. Let's turn that down. Now I'd have to bring that up actually. Let's AC couple that and bring it back in the center. And then you can see the power, and if you look down the bottom here, you can see the peak-to-peak ripple that I'm getting. And if we zoom in a little bit, you can see that there is some amount of noise there. Now, this is not really the way you're actually supposed to measure this, and I'll link in the way you actually are supposed to measure. But effectively, you're actually supposed to measure across the output filtering, which is the inductor and the capacitor, and use your little high frequency ground point on the tip of the scope probe, because you're generating a bunch of capacitance here, you're generating a bunch of magnetic fields with regard to the load and so on, and there's quite a few steps that you need to go, or a reasonably rigorous process you're supposed to go and properly measure the ripple here. But for ballpark figures, where I did the back of my calculations against the data sheet, I should get around 30 millivolt. I'm seeing around 30 milli. I'm in the ballpark, so I'm happy with the output of that device. So there you go. I took a journey from having a need to build a heater, going through the design and creation of the project, to developing the PCBs and actually creating a working unit and showing you some of the tests for it. So it really was, to me, a better way to try and get experience with some of these things like creating clean automotive power, surface mount componentry, the assembly process, and so on. And so even though the final outcome is a ridiculous solution to the problem, it's still something that I really appreciated and I really enjoyed working on. Even something as simple as this when I get a chance to go and do it. And I've been really just doing it in 10 or 15 minute slots that I've had some time over the last several months to go and create this. Anyway, last thing I wanted to show you just before I went off, as I talked about measuring supply ripple correctly. This is a nice little E Times article on it that explains some of the problems there and how you're actually supposed to measure it. And here you can see the measurement across the output capacitors there to be able to give you the better measurement. But really take a read of the whole article there to get a good grip on how to measure the final outcome, the final ripple in a power supply. So hopefully you've had as much fun in the maker world and doing these ridiculous type of things as I had. And I look forward to what I have next or what I see you guys do. Thanks. Bye.